Alessia Franchini from Milano about electromagnetic counterpart of sub-parsec massive black hole binaries. So please.
Thank you.
Alessia.
Thank you. Can you all hear me? Fine? Okay, great. So first of all, I would like to thank the organizers for inviting me and for organizing this great meeting. So yeah, I'm gonna be trying to give like an overview of the electromagnetic counterparts that we can expect from massive black hole binaries at all scales. So I'm gonna also touch upon the dual AGN and you know, the kiloparsec separated binaries that Marta briefly mentioned before. Okay, so just I don't think I have to go through this slide in details, but just for reference, when two galaxies merge, the black holes at their center are supposed to form a binary eventually through several processes. So we have first dynamical friction and then loss of angular momentum through interaction with either stars or gas before gravitational waves can take over and drive the merger. I just wanted to mention like the few stages that the binary goes through during this process, because the observational techniques and methods used to find candidates through electromagnetic emission change depending on the scale. And I would argue that the farther you go, let's say to the left in this plot, the harder it gets to find them. So basically during the galaxy merger, then the first phase, let's say, can be identified by the coalescence of the two galactic nuclei and a formation of a pair separated by a few kiloparsecs. Then stage 2, you get to the formation of a proper binary at parsec scales. Stage 3, the binary can harden via either gas or stellar interaction, going from 1 parsec to 10 to the minus 3 parsecs. And then finally, you have in spiral and coalescence through gravitational waves. So this is the first to second stage. So this is a nice survey. It's quite outdated, but I just wanted to show you that you can, in stage 1 to 2, so when the two objects are kiloparsecs separated, you can distinguish them in many bands, mainly X-ray and optical. So you can see here, BAT-select detected dual AGN identified by different colors depending on the band where the AGN part was detected. And then you can see like the counterpart of single AGN, again from the same survey. And so basically through these surveys there have been identified 200 objects, but the dual AGN frequency is roughly 10% at very low redshift, so very nearby. And as you can see, this is a pretty nice image of basically O3 oxygen 3 emission of a dual AGN, and here the separation is even smaller than a kiloparsecs, is 400 parsecs or so. Then one other way where how people can identify dual AGN is through double-peaked emission lines from oxygen 3 in the spectra. And this is being used for kiloparsec to sub-kiloparsec scale. So basically the main idea is that each of the two AGN has its own narrow line region, which is a region that extends to more or less one kiloparsec from the central engine. And so basically, then these regions trace the relative velocities of the two components that orbit each other. And so you expect the emission line to have two peaks because you have a dual AGN. So you would think that this is a kind of a robust technique. Unfortunately, it isn't. So I show you here two clear examples of why this is not the case. So you can see that in both examples, you kind of have this double-peaked oxygen 3 emission line, but while on the top, there is clear evidence of another core close by, on the bottom, you don't see anything else. So there are other processes occurring in narrow line region, even of single AGN, that can give you a double peak emission line. And this has led to the discovery of this big class of objects known as double peaked emitters that are not all, of course, dual AGN. So even at kiloparsec scales, it's still challenging to identify and pinpoint dual AGN. This is one of the best examples of successful, I would say, identification of a candidate at stage 2. So it's much close to parsec scales. So this is radio images from VLBA of 2 flat spectrum radio cores. This is the name of the source, 0402, and it's composed by radio galaxies and an elliptical galaxy featuring basic. So these discovery papers argue that this is a binary separated by 7.3 parsecs with estimated masses about 10 to the 8 solar masses, and then you can compute the merger time scale accordingly. So I would say that this is one of the successful identified candidate just through radio observation, just because the binary is still separated enough that you can distinguish the 2 radio cores. So as I mentioned earlier, the techniques that can be used and also their affidability changes with separation. So going from 1 parsec, where you switch from the, let's say, pair massive black holes to the proper massive black hole binaries, all the way to merger, essentially. So here I just identified the ballpark estimate of the Lisa band, and these are all the observational techniques that have been so far used, and I distinguish between photometry and spectroscopy. So. Yeah. So I mentioned that when the binary is sufficiently separated, you can identify the 2 candidates with the VLBI. Then let's say there are again several techniques, mostly spectroscopic, to identify candidates. So probably the famous one is through the observation of the broad iron line emission line, in the X-rays, and this can be used actually throughout basically the whole range of spatial separations. Then you can look at line ratios, so the ratios between the intensity of different lines, and this can also be an indication of whether there is a binary. So one of the 2 AGN is obscuring and changing the emission of the other broadline region. Then you can identify candidate through velocity offset in the Balmer lines, and this has been widely used by Mike Heraclius and Jesse Rannaud. And this is possibly one of the strongest ways to identify candidates. Recently, Jesse has also a very nice paper looking at UV lines with similar shifts in the Balmer as the Balmer lines, and this is also a strong indication of the presence of a potential binary. Then if you then this is a kind of new technique that Massimo Dotti's group in Bicocca has been developing. So looking at the broadline region response to the continuum periodic variability due to the orbital motion of the 2 objects. Then you can look at the inflection, so the notch that Marta also mentioned before in the spectral energy distribution. And then, or you can look at photometry. So of course you can identify the chirp, but only when the binary is very close to merger. Then you can look for Doppler boosting. So again, 2 objects orbit each other, and this creates a Doppler boost in the continuum. And then you can look at precessing radio jets, but there are a lot of things that can drive precession of jets that are not necessarily binary. So I would say that this is a bit more uncertain as a technique. And then you can finally look at the famous afterglow that was proposed, that was identified back in 2005. In the X-rays mainly, essentially. So the 2 binaries have a cavity. Each one of them has its own accretion disk. Then when they merge, the accretion disks are gone, and you have a sudden drop in the X-ray. So I would focus on this more later as it's the part that I've been recently working on. And I just mentioned that this is so this is the scale that holds for a 10 to the 6 or mass binary at sub-Eddington accretion rate. So basically, yes, this slide basically sums up what are, I think, the two main, the strongest ways and most secure ways to identify candidates. One is spectroscopic and the other is photometric. So spectroscopic wise, I think looking at broad emission line velocity shifts is still the best way to identify candidates. And doing these, performing these analyses, basically there have been identified single peak emitters velocity offsets in the H beta broad line with respect to the narrow line region, an indication of the presence of a binary. And there have been 3 candidate sub-parsec massive black hole binary identified through monotonic changes in the radial velocity curves of actually one of the shoulders of the H alpha line. And then again, I just want to mention again this recent paper where they show that they have UV lines in the UV that show the same velocity shifts as the Balmer lines. And then the photometric part is also very interesting because you can look into periodic modulation in your light curve. And especially you can exploit the new optical capabilities of Vera Rubin and the Zwicky transient facility. And the only problem with this method is that the periods that can be probed, that need to be probed, are quite long. So there is only a certain range of separation that you can probe with these techniques. But possibly this might give you a unique signature of the fact that you're looking at a binary, a supermassive black hole binary. So these are 2 examples of potential candidates at sub-parsec scale that have been then discarded in the literature. So this is possibly one of the famous objects is J0927. It was proposed to be either a recoiling supermassive black hole or a candidate massive black hole binaries because of the blue shifted broad emission lines that you can see highlighted here. And similarly, also this object showed the same characteristics, together with the presence of a weak red wing of the H alpha line, which is this line here, and so, but then this object was very soon discarded and was basically shifted towards the class of double peaked emitters that I was mentioning before. But still, I think, using these techniques, this technique is still the best way to identify candidates. And to confirm the candidates, you ideally want to have 2 different techniques, possibly one spectroscopic and one photometric, apply them to the same source, and then identify candidates. And also, I forgot to mention, but quickly, maybe you already know, OJ287 is also a binary candidate, and also PG1553, I think. So this is actually the object that I was showing here. So this was, again, proposed as a massive black hole binary candidate, but then a photometric study of the field image did not find any galaxy cluster, so it didn't find like a companion, a clearly identifiable companion. And this is further supported by HST images, as you can see here. And basically, this is the CO emission map that shows a lot of molecular gas, but basically this allowed to discard both the recoiling and the massive black hole binary hypothesis for this source. So this is another candidate that was proposed 3 years ago now. I don't know if you heard of it, but it was the famous TikTok object that these people thought was merging massive black hole binary. So you can see the evolution of the period. So like the chirping signal, let's say, yeah, the proposed chirping signal, and it would have merged basically like in 1 hour, or yeah. Exactly. So this was puzzling, and then what we did in this paper was to get more observation in the optical of the same source with the REMS telescope, and so basically you can see the new data points that are these ones in orange, and you can see that you can basically safely discard the hypothesis that this is actually like merging soon massive black hole binaries at subparsec separations. Okay, so as I said, during the evolution of binaries through cosmic time, they eventually need to overcome the parsec scale separation in two possible ways. One is stellar hardening, so the hardening through stellar interaction. So single stars pass by and extract angular momentum from the binary, and this leads the orbit to shrink, or they interact with the gaseous environment, so a circumbinary disk, basically formed by the gas that is containing both galaxies that merge and eventually ends up close to the binary in the central region. So this is just a plot showing this is a bit of a detail of the modeling of binaries in the gaseous environment. So you have the black hole binary mass and separation. This is again for 0.1 Eddington fraction. And you can identify basically 3 regions of this parameter space where according to in each different region is the gravity of the gas onto the binary is either important or you can safely neglect it. And this has an impact in the simulation community. So when you want to simulate the interaction between a circumbinary disk and a massive black hole binary. So essentially, if you look at LISA binaries, so mass is below 10 to the 7, you are in this gray region here, and you can safely neglect the disk self-gravity because it's not dominant. Below this black line, you are in the already in the GW-dominated regime, so you really don't care what the binary is doing with the gas. It's gonna in spiral. Of course, you care about electromagnetic counterparts, and I will go back to that later. And then in this other region, which is maybe more relevant for pulsar timing array binaries, then the disk self-gravity might be important. Although recent observations suggest that PTA sources might reside in relatively empty, relatively gas-starved galaxies. But so yeah, so if you assume that a PTA source, a PTA massive black hole binary is actually residing in a gaseous environment, then you need to take the disk self-gravity into account. And so if you do that, so this is a numerical simulation that I ran a while ago, including the gas self-gravity. And so you can see that the disk morphology is quite peculiar. So the disk is if the Tumbre parameter, so the parameter that tells you whether the disk is stable or unstable to let's say gravitational collapse, gravitational instabilities technically, then you have these the formation of these spirals, and these spirals basically are able to remove the angular momentum from the binary and drive the binary towards coalescence. This is actually how the disk looks like for different binary parameters. So you can see that the structure is very different, but still you can look into what is the effect of this kind of disks on the binary accretion rate to potentially identify periodicities in the light curve. And this is This is actually a nice, let's say, exploration of the parameter space. It's still limited because these are full 3D hydro simulations, so they're quite expensive, so we cannot explore much the parameter space. But I will just point out that basically we chose different values of the mass ratio of the binary and different initial eccentricities, and we can see that the binary always in spirals with time. And yeah, the eccentricity is a bit more complicated. You have some instances where they saturate around the same value and some instances where each binary will retain its own initial eccentricity, regardless of the interaction with the disk, essentially. Then what you want to look for photometry is what kind of periodicity can you expect from a binary that is accreting from a circumbinary disk. So here we took basically the same simulations of the previous slide, and we looked into the accretion rate onto the binary components. And so these are a fast Fourier transform of the accretion rate onto the binary. And you can see that depending on the choice of binary parameters, there are different periodicities that pop up. The main interesting ones, I would say, are the one at the orbital period of the binary, so associated with the orbital motion of the binary, and at twice the orbital period of the binary that you cannot see here because it's the plot is cut here. But still, it's of has a lower amplitude, but still might be identifiable. And then the interesting part is this one here. So at lower frequencies compared to the binary orbital frequency, so longer orbital period, which is associated instead to the periodicity, to the disk inner edge. So basically the orbital motion of the disk inner edge, as it is basically the main source of streams of material that can enter the binary cavity and then eventually accrete onto the binary. So this is important because if you look for periodicities in your light curve and you can identify both an orbital periodicity and a superorbital periodicity, then I would say it's a smoking gun that you're looking at the binary. So instead, if you move to LISA sources, where again the disk can be as smooth as possible, not gravitationally unstable, then you might have even more disk morphologies. So what we did here was to perform again 3D hydro simulations with a particular technique to resolve the motion of the gas inside the binary, the cavity carved in the disk. And I would say the important part for electromagnetic emission is to look into what happens when you change the disk temperature to the gas dynamics, essentially. So basically, this is like a relatively cold disk, and you can see that from the aspect ratio, which is more or less so it's a disk height over the disk radius, and it's an indication of the disk temperature. So this is a much colder disk, and you can see that the dynamics. So we have very little material that is able to enter the cavity, and you can see that these overdensities are much more pronounced than in other cases. This is possibly the largest, the more widely explored parameter space, so intermediate temperature of the gas. You can see there is the amount of gas that enters the cavity is significantly higher, and still you form this kind of overdensity at the cavity edge, which is named lump in the community, and I think Raphael is going to talk more about what this does to the electromagnetic emission. And then finally, if you have a very warm disk, then basically the binary is not able to carve a cavity efficiently, and so you have just gas inflow into the disk, and so you are left basically with a very symmetric distribution of gas, and nothing particularly interesting happens. With these simulations, you can actually follow the in-spiral through both gas torques and gravitational wave emission all the way to the merger. And we did that by implementing post-Newtonian corrections up to the 2.5 post-Newtonian order in order to take into account both conservative and dissipative effects. And essentially, we did the same. We did this test for both like a higher temperature disk and a colder disk. You can see here the evolution starting from 30 days to the in-spiral all the way to the merger. And And you can see that the morphology is very different between the two cases. This is a much colder disk, and you can see that the lump part, so this overdensity, is retained basically all the way to merger, and the cavity is way more eccentric than in this case. So from this simulation, what you can do is to assume that the disk is going to emit a black body. I know this is like the most simplistic assumption. Is the reality is much more complicated than that, but bear with me. And so you can look into what happens at the flux in different bands. So the emission from the disk in different bands when the binary merges. And you can see that on the left side, you see the warm disk simulation. On the right side, the cold disk simulation. And here, we basically reproduce the well-known famous afterglow, which is reassuring. So you have the X-ray flux here in cyan. And then when the binary merges, you have a sudden drop by 2 orders of magnitude in the X-rays. And contemporarily, the UV flux increases because the cavity is shrinking around the binary, that it's not a binary anymore, essentially. But then if you look into what happens when you have a cold disk, so you have very little material in the cavity, so you don't have this huge drop in the X-rays. Actually, the flux in the X-rays is severely suppressed because you have so little material, and the drop is not as sudden as in the warm disk case scenario. So identifying candidates using if they evolve in colder disk, you can more or less forget about the afterglow. Or at least it's not going to happen on so fast time scales. Here we wanted to look at the chirp. Unfortunately, we couldn't adapt the time step of the simulation to the in spiral. So this is why they look so weird. So you have this is a spectrogram of what happens to the frequency in the optical band, again for a warm disk case. And here, this line specifically is actually the chirping of the inner edge of the circumbinary disk. So this also can be a good signature to look for when searching for massive black hole binaries. Then, in the interest of time, I think I'm gonna skip that. But we did a couple of experiments with kicks, with kicking the remnant either off plane or in plane to see what happens to the accretion rate. This would also be interested maybe to identify post-merger candidates, even though it's much complicated. And then what we did next was to study, so we went back to the scale where gravitational waves are not dominant yet. So this is milliparsec separation. And these are much more complex simulation. They include more physics than the isothermal simulation that I showed you so far. But what we looked for are periodicities essentially in the optical bands that are going to be explored by Vera Rubin for different binary orbital parameters. So here you have a circular boring equal mass binary, and this is like a very eccentric, very unequal mass binaries. Again, this is redshift 0.1, so it's very close. And we also took into account the noise that Vera Rubin is going to have in these bands. So you can see that if the binary is circular and equal mass, then basically the predominant periodicity that you can look for is the superorbital modulation of the cavity edge, which is harder to find because of the periods that you need to probe. Or and possibly the second more interesting is, at least in the optical, is the periodicity on twice the orbital period. Again, half the orbital period, again related to with the motion of the binary inside the cavity. While if the binary is very eccentric and unequal mass, then you have a predominant modulation on the binary orbital period. So in principle, you can do reverse engineering and say, okay, I identify a periodicity which I can relate to the binary orbital frequency. If this is basically the predominant one, then I'm looking at an eccentric or unequal mass system. Of course, reality is much more complicated than that, and I think this is not a very nice plot to look at, but it's very informative, I think, because so what we did was to take the same simulation that I showed in the slide before, and say, okay, we have a binary that have a 1 year orbital period. So in 10 years, 5 years of Vera Rubin, there's only so many orbits that you can probe. So what happens, like the fast Fourier transform that I showed you here are computed over hundreds or even thousands of binary orbits. And this is why they look so nice and the peaks look so sharp. But then if you only have 5 orbits and a circular equal mass binary, there is clearly no hope of detecting any periodicity in Vera Rubin. You can have some chances if you have 50 binary orbits. So there is a limited range of separation that you can probe with photometry. And the situation is slightly better if you go to an equal mass or even eccentric system, but still, if you rely on only 5 orbits as your time scale, there's no way you can probe these systems. So yeah, so these are basically sum up all that I said before. So I leave it here, and I'll thank you for the attention and happy to take questions.
Thanks, Alessia. So time for question.
Thank you. Great talk. I have a few questions just out of curiosity. So one is, how do you model the X-ray and optical emission in the simulations? And so what is the nature of this X-ray afterglow that you mentioned? You had this nice simulation with PN corrections here.
Yeah,
exactly.
Yeah. So okay. So this is possibly this is very simplistic. So we take our isothermal disk. So first of all, it's isothermal, and this is already a great, like a big assumption. The simulation that I showed after are not isothermal, but yeah. But anyways, so we assume that each particle in the simulation radiates as a black body with its own temperature. Then we compute the effective temperature, assuming some opacity, and then we compute the light curve. So really the simplest thing that you can think of. And the afterglow is actually due to the fact that in this case, you see that the cavity is closing around the merging black hole. So basically, you have in the last day, the mini disks disappear. They are completely accreted. The binary merges. And then the cavity, since the disk is very hot, so it's very viscous, just suddenly close around the remnant and switch on accretion again.
Okay.
Or at least, I mean, it gets close to the remnant, so your X-ray flux increases. Yeah.
Makes sense. Thank you. And very last question, going back to this TikTok object. So what's your favorite explanation?
Oh man, this is a tough question. I don't know. I haven't thought of that, but I will think about it.
Thank you, Alessia. Another question?
Thank you for the talk. Just maybe, what about the recoil, the post-merger recoil after the binary merges? Does it play a role in the afterglow?
Sorry, say again?
What about the gravitational recoil that is imparted in the remnant black hole after the coalescence?
Yes.
Does it change the picture for the afterglow or not?
Okay, yes. So this is what we tried to do, imparting kicks to the remnant. So yeah, as you can see here, there is a delay between your drop in this is accretion rate though. It's not I haven't calculated the luminosity. It would be interesting to do that. But essentially there is this delay due to so this is the colder disk simulation. So the cavity takes longer to close, and this is why you have a longer delay in the switch back on to the accretion. But the interesting part is that so the purple line is identifies the off-plane kick of the remnant. So the remnant is basically kicked off-plane, so in the z direction, and drags the disk with it. And then the yellow part is instead what happens when the remnant is kicked in the direction of the disk. So we can see this different in like accretion rates. So in the first case, the accretion rate rises way more quickly. Unfortunately, since our binary was equal mass, circular, and spinless, in principle, you don't have kicks. So we had to use like the lowest velocity of the kick, just because, so we don't get like dramatic, let's say, effects. But that would be that's on our list actually to explore this more. Yeah. Thank you.
Alessia, time for more questions.
Hi, thank you ever so much for this talk. It's really important work so that we can actually identify these binaries, especially before LISA. One question was actually about, oh, I've lost its name now. I wrote it down. So it was the SDSS J0927 that you showed right at the beginning, almost. It was like one of the first few slides. And you said that there was evidence in the lines for binarity, but when they looked at the optical, they didn't see any evidence for two objects.
Yes.
Is this so surprising? I mean, what is the separation of the two objects? What was the projected separation? Because often we've also looked and you just see nothing. I don't know. I mean, I don't know what the resolution exactly of the data is, but
that's a good question. I'm not an observer, so I really don't know. Yeah, I don't have an answer to you on the top of my head. Sorry.
I'll note down those references. I can have a look.
Yeah, I have to look back at the paper. Yeah.
It's really not so surprising. I don't think, not from what
No, I agree. Like in principle, you need at least two techniques that tell you the same, that gives you the same evidence to identify a candidate. I don't think you can do it with only one on any scale.
Okay, I think we have time for one last question. No, if not, I have one. In fact, at the beginning, you said that the fraction of dual AGN is about 10%.
Yeah.
So it is a fraction about the population of AGN or the population of the full galaxy, the full galaxy.
I think it was just a fraction of the population exploring the BAT survey. Okay. I don't think it was like anything more than that. Okay. Yes, yeah. So they probably targeted, you know, yeah.
Thank you, Alessia.
Thank you.
Thanks again, Alessia.